On the banks of the Susquehanna River in Columbia County, in the northeast corner of the state of Pennsylvania, just outside the town of Berwick, population 10,355, lies a nuclear power plant. As you drive down Route 11, you can see the steam pouring out of its mammoth towers over the tops of the trees. This is the single source of power in the area for a 20-mile radius. That means the 2,500 megawatts of power it generates must cover an area of 1,300 square miles and convert for every possible need within that geography. Columbia County has a little over 64,000 people. Of all the energy we harvest and generate, we lose more than two-thirds of it due to transmission, conversion, distribution, and what experts call rejected. This may not seem like a big deal in the Pennsylvania countryside, but try a metropolis like Manhattan or the entire energy needs of a country like the United States, and you're talking about a hemorrhaging of money and efficiency. One of the pillars of modern society, the power grid, teeters on the brink of obsolescence. In this realm, vast amounts of energy are generated only to be squandered through inefficiencies, unidirectional flow, passive transformers, and countless conversion points. It is a system that is in danger of outliving its usefulness, struggling to meet the demands of an increasingly electrified world. Recent news stories have highlighted the challenges faced by our aging power infrastructure as it groans under the weight of the terawatt hours required to power our cities, our transportation, our ever-growing array of personal electronics, and smart homes. Don't forget a little thing called AI. But amidst this landscape of inefficiency and waste, a glimmer of hope emerges. Distributed energy resources, solid-state transformers, and innovative storage solutions, powered by the likes of silicon carbide, offer a path forward. By harnessing these technologies, we can preserve the power we generate, ensuring that as many watts as possible are used to their fullest potential. It's a world that's not too far away, but we have a choice: to cling to the vestiges of a bygone era or to embrace the promise of a more efficient, sustainable future. With each passing day, the imperative grows clearer. We must adapt, we must innovate, and we must evolve for the sake of our planet and the generations to come. As we enter the third wave of silicon carbide, some big ideas are propelling what could be a very prosperous future. How can microchip technology help fix the inefficiencies of modern power grids? Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience. Our guest today is Dr. Kevin Speer. Kevin is the Silicon Carbide Technology Director at Microchip Technology. He joins us today from our headquarters in Chandler, Arizona. Welcome, Kevin. Thank you for joining Beyond the Microchip.
Thank you, Dana.
In the intro, we briefly talked about the terrible inefficiencies of our modern power grid infrastructure and how some novel ideas about power management could help solve the growing concern over our increasing power needs. Tell us about it.
Thanks for having me, Dana. I think the biggest challenge that we have today is awareness. When we look at the power electronics, and as other people will say in other episodes, this community is talking all about efficiency at the point of load. Whether we're referring to electric vehicles, whether we're talking about motor drives, whether we're talking about solar farms and the string inverters that deliver the power from the solar panels to the end user, all of these can be thought of as the final destination that the electrons take on their journey from harvest to consumption. And that's fine. These are absolutely things that we need to make more efficient. But at the top of the episode, like you said, we are losing a third of the electricity we generate. So I feel like we need to start paying attention to that as well.
I'm sure a lot of people don't understand that. The power grid is designed to capture it from the plant and deliver it to the neighborhood, the industrial park, the commercial facility. There's a lot that goes on between those 2 points, right?
Oh, yeah. So typically, at the generation point, you're talking about hundreds of kilovolts, which clearly is unsafe for humans to be around.
Right.
So in order for the electricity to be at a level that is safe for humans to use, in other words, the power outlets in your home, for example, we have to take those hundreds of kV down to 110, or in other areas of the world, 220 volts AC. So you're basically dropping the power level or the voltage level by 3 orders of magnitude. That has to be done through conversion. And the efficiency of that conversion is really what we're talking about here. We lose so much power, especially when we get to the converters at the lower voltage levels, which means at the point of load. And again, circling back to that, we absolutely need to make those things more efficient. And in fact, silicon carbide is doing that. Whether it is extending the range of an electric vehicle by using silicon carbide instead of the silicon IGBT. It could be achieving the higher grades of data center power supplies. Silicon carbide is making inroads there. It's making efficiencies and power densities possible that silicon could never dream of. So those things are absolutely important, but we're also talking about efficiency improvements that save hundreds or thousands of watts. Sounds like a lot, but when we go up to the grid scale, we're talking about megawatts, terawatts of savings. And I just feel like we are paying too much attention to efficiency at the point of load, and we're not looking at the bigger picture of how the energy gets there to begin with.
Right. So you mentioned that word terawatt. That came up when I talked to Clayton. We have a watt, we have a kilowatt, that's for those of you that like the metric system. A kilowatt, a megawatt, a gigawatt, and a terawatt.
Yeah.
So what is a kilowatt power?
So a kilowatt, you can imagine, would be like a hairdryer.
Okay. All right.
Right.
So 1,000 hairdryers gets you to a megawatt.
There you go. Yeah.
And then from a megawatt, you get to a gigawatt. What is a gigawatt power?
A gigawatt, that's a lot of power. Right. If you think about a single wind turbine, like an offshore, one of these really, really monster wind turbines that are out in the ocean delivering power, those are 5 to 10 megawatts. Okay. So you would need 100 of those to get to a gigawatt. So it's a lot of power. And then a terawatt is 1,000 times that.
Right. So we're talking orders of magnitude here beyond a hairdryer.
Several orders of magnitude, yes.
We're talking about millions of homes per year.
Yeah. And in fact, millions of homes per year. So the power that we lose just from transmission and distribution in the United States would be enough to power 1.5 million American homes for a year. Just the power that we lose.
And that's just disappearing up
just gone. Just gone.
So I'm sure anybody listening to this might be a little upset when they look at their electric bill, knowing that all that is just going up into rejection and waste. So we're looking at terawatts of power, and we have a number of different generation sources. We've got wind, we've got solar, we've got coal, natural gas, geothermal. You mentioned wind turbines. There's also, I hear they're looking at doing things like ocean waves.
Tidal power.
Yeah. Tidal power. Okay. That's all methods of generation.
Right.
But then you got to take that and you got to transfer it.
Yeah. So got to go somewhere.
So all of that, when it's going somewhere, that's the problem then.
Yeah. And again, back to your point at the top of the episode, you described I think you said 1,300 square miles was being served by a single power plant. That too is part of the big picture problem. When you have centralized power generation, you have no choice but to transmit it over long distances.
Right.
And a lot of those centralized power generation sources, coal-fired power plants, even the mildly controversial nuclear power plants, those things have been our power source forever. But as we start moving to a more sustainable power delivery and consumption landscape, we need to start integrating distributed energy resources. And this is what you're talking about with solar and wind and all the other generations. And there, what's the difference? Well, there we don't have to have a monster power generation source in one place serving a really large area. Instead of that, we can put a solar farm, or even, and let's use the example of a single residence. Put solar panels on top of the roof, and now you've sort of got your own little microgrid. And the fact that power generation in the future is going to be so decentralized, Well, that's great so that power doesn't have to travel long distances, but how are we going to bring those distributed energy resources into the grid? They don't talk the same language.
Right. So get into that. What I was very interested in what you were talking about was this
Omnidirectional grid.
Omnidirectional. Yeah. Can you talk about that?
Yeah. So today we have, like we were just talking about, you've got all of your main power coming from a centralized source, and it's serving a very large area, large population that is almost always far away from where the power is being generated. One benefit to that is that those power sources, we're used to them. We've been using them for years and years. Now, of course, we've talked about all the power that's lost in this situation, but we know how it works.
Right.
Okay. We've come to terms with the power that we're losing. When we look at wind and solar and some of the other emerging energy resources, they don't have the same voltages, the same voltage stability. Some of them may be DC instead of AC. If they're AC, they'll have different frequencies. A problem that's known to many is solar. Sun isn't always shining.
Yeah.
The wind isn't always blowing. So there's a lot of questions about that. And that's what puts energy storage systems on the radar.
Right.
But to incorporate all of these different energy sources that have different voltages, different frequencies, we have to make our grid intelligent. Today it's not. And power only flows one way.
Right.
Right. With solid state transformers using semiconductors to do the power conversion instead of the archaic equipment that we have in the grid now, we can start to do that intelligently. We can, the fact that these distributed energy resources have different voltages, different frequencies, that's okay because solid state transformers can deal with that.
Right.
Right.
Versus the passive ones we have.
Right. And then the other point is solid state transformers using power electronics for distribution in particular, and eventually transmission, that allows for bidirectional flow at that power stage. And then if you map that into a bigger grid, you've got an omnidirectional possibility. You can have your electric vehicle parked in the garage, plugged into the charger, and it's not just taking energy from the wall, but if something else in your home needs the power, it will take the energy from the battery in the car.
So sending it back. Yeah.
If you choose.
Okay.
So that's the omnidirectional grid in a home setting. And if you can imagine putting that in a metropolitan setting, in a statewide setting, country setting. And then another big benefit is with silicon carbide, you can make the transformers so much smaller, so much lighter. And now you have the ability to, one of the things that I saw when I was preparing for some of these talks is 1 out of 10 people in the planet still does not have power access. I was blown away by that.
Yeah.
And the problem, I believe, the reason why that is because of all of our centralized power generation. Now, if we can go to a more microgrid, distributed energy resource friendly, using solid state transformers, I don't think that's going to be such a problem anymore.
So you're talking about bringing the power where it's needed on demand.
Right.
Some of these solutions would allow for perhaps feeding later time zones. If you're in a kind of a horizontal plane, like the United States, we could have, correct me if I'm wrong here, but we could have the California sun feeding the New York night if we had the connections possible.
Yeah. And
I'm not jumping too far out here, am I?
No, that's fair. I mean, when we talk about the omnidirectional grid, when people say, well, what do you mean? We say it's simple. We want to be able to get power to anyone from anywhere at any time. And today's grid can't do that. And I think that's the duck curve that you're referring to. One other thing that is going to be different in the grid of the future is energy storage systems.
Right.
And that greatly mitigates the impact of the duck curve, right? Because maybe The sun in California doesn't have to feed users in New York because users in New York will have stored surplus energy in the energy storage systems.
They'll have storage. Yeah. Can you talk about those storage systems? Are we just talking big wall batteries or?
Pretty much. Yeah. Okay. I mean, of course it depends on the power capacity that's needed. You can imagine an energy storage system for a home might just be a wall mounted type of situation, whereas energy storage for a major microchip fab may be quite a bit more substantial.
Right.
But yeah, I mean, the purpose is the same. It is to embrace distributed energy resources and use that energy, and what you're harvesting that you're not using, just slough it off to the energy storage system so it's there for you to use later.
Right. Hold on a minute. Right.
Yeah.
Okay, so we've got solid state transformers, we've got DER, distributed energy resources, and we've got storage. And this kind of leads us down into why we're talking to you today, which is silicon carbide. Now, you mentioned IGBTs before. Those are just different methods of power, right?
It's a little bit more complex than that. So the IGBT is an insulated gate bipolar transistor, and it has become pervasive in the world of silicon and high voltage power conversion. It was first introduced in the early 1980s. Since then, it has now become available from, a couple hundred volts all the way up to 6,500 volts. Mm-hmm. So it is the IGBT, the silicon IGBT is absolutely the workhorse of high voltage power generation, power conversion. Silicon carbide comes in and takes care of the imperfections that the IGBT has.
Okay.
The IGBT was created because the silicon MOSFET couldn't block high enough voltages and work efficiently enough. It can block high voltages. It's just not worth using. So the IGBT was conceptualized and developed to take silicon MOSFETs up to the higher voltage capabilities. The drawback with the IGBT is it's very lossy at high switching frequencies. What's the problem with that? Just you use lower switching frequencies? Well, if you use lower switching frequencies, stuff gets really, really big and heavy. And we're talking about semiconductors here, I realize, and we're all probably stuck in the tunnel vision of the cost of silicon versus silicon carbide. But let's not forget, when you're talking about a big conversion system, especially the high power ones that we're talking about here, most of the cost is not in the semiconductors. It's in the passive components. Right. It's in the iron and the copper of the transformers. So silicon carbide comes in and allows you to block high voltage and use higher switching frequencies. So that is the big difference. And silicon carbide, just in somewhat generic terms, will slash the losses of a silicon IGBT in a given power conversion system by 70%.
Ooh.
70%.
So we're taking an already lossy process and we're bringing some of it back just through efficiencies in switching and conversion.
That's right.
So obviously that's why it's useful. What devices or solutions could apply to some of the applications you're talking about today? Is there something in the portfolio either now or in the future that would perform these tasks?
So it's going to be an evolution. We've talked a lot about point of load, and I talked about it in I hope it wasn't a derogatory way. Again, like we should be making point of load converters more efficient.
Right.
Silicon carbide is doing that already. It has silicon carbide got a really big boost when the electric vehicle market started adopting it for the traction inverters to extend their range. But at the 600, and that's primarily 650 and 1200 volt class products.
Right.
650 and 1200 volt class silicon carbide products have been on the market now. Diodes have been out since 2001. MOSFETs have been out since 2011, 2012 timeframe. These products are finding their homes in making electric vehicles more efficient, whether it's the drivetrain, the OBC, DC-DC converter. It's not just automotive, industrial applications. Many of them are using 650, 1200, some 1700 volt devices. These are being used in solar inverters to make them much more efficient. Industrial motor drives, a variety of industrial applications. Silicon carbide now calls home. So silicon carbide is making great progress in point of load up to 650, 1200, 1700 volt classes. Okay, and that's in power discretes and also power modules. Those products exist today,
right,
and are available from multiple suppliers.
Okay.
Going forward, to get to modernize our grid, we will need higher voltages. Microchip, a little over 2 years ago, was one of the first companies to release to production a 3.3 kV silicon carbide MOSFET and diodes. And we had pretty good die sizes too. I mean, we have a 25 milliohm bare die at 3.3 kV in the MOSFET, and we have a 90 amp Schottky diode. So these are die that are suitable for high power conversion, even at these voltage levels. When you start to go to grid scale, if we talk about going back to the power generation, it's hundreds of kV. Then it travels many miles, and there it stepped down to maybe tens of kV. That's where silicon carbide is ready to start being developed for prime time today. Is at the substation level.
Got it.
And the International Energy Agency will, they have said that it would be, it would probably be reckless to develop 100 kV silicon carbide power devices. What we need to do instead is we need to develop the voltages suitable for substation, distribution substations. And if we do that, it will be like a domino effect. We'll prove the technology. It will go up in economies of scale. More and more suppliers will be there to give us the materials we need to make the devices. And then it will just proliferate across the system. But for those distribution substations, they will tend to be, let's say, 35 kV. It is possible, Dana, to use a 1200 volt, 1700 volt, 3.3 kV device, and you just stack them in series to meet the voltage you need. Problem with that is every single device has to have a control, a gate driver. And if you're using all these devices in series to block a really high voltage, you had better make sure they all turn on and turn off at the same time.
So not entirely scalable.
Exactly.
Easily.
It's not easy. It's very, very challenging. And there are points of failure. Nobody wants the grid to fall out,
obviously
right?
Not like Texas back in 2021.
Right. So these solutions must be extremely reliable, and to get to the point of reliability, you want to series connect fewer devices. So like I said, you can create a solid state transformer solution for a distribution substation using today's commercial devices, but it's not ideal. We need to go from what's currently the 3.3 kV device rating class. We need to go instead up to a 10, 12 kV, and even higher.
That's all part of conversion.
Yep.
We've been kind of talking about the future. So at this point in the show, we usually ask you if you have any predictions about the future. What I'll do instead maybe is, we know that our electricity needs are going to go up. So is it simply solved by conversion efficiencies? Is it material science improvements? Is it more power plants? Is it all of the above? What are we going to need to solve this problem?
The first two things you said, absolutely. The more power plants, I agree with that, but I want to change the word a little bit. It's not more power plants, it's more distributed energy, right? It's fewer centralized power plants and more decentralized power plants. To make these high voltage devices, we do need materials. One of the challenges with a high voltage silicon carbide power device is you need really thick epitaxy, and it's very difficult to grow high quality silicon carbide. I mean, the growth temperatures of silicon carbide are 2,500 degrees C. That's half the temperature of the sun.
Yeah.
So it's where we will need materials research and development for the thick epitaxy. Challenges with thick epitaxy will include, number one, the growth of it. Remember, when you're growing silicon carbide epitaxy on the wafer, it's also growing on the chamber. So you have to clean the chamber, and it is very, very difficult to remove silicon carbide.
Especially at those temperatures.
Yeah. So that's the first problem. The second problem is growing that thick of epi without crystal defects. The third problem is the stress that is placed on the wafers when you grow this thick of epitaxy that may cause the wafer to change its shape. In the silicon carbide materials community, we frequently talk about wafers potato chipping. Mm-hmm. Literally, they will bend and curve. And imagine trying to do photolithography on a potato chip.
On a curved surface, yeah.
So there's a lot of challenges on the material side, but they're not insurmountable. These are things that we're overcome in silicon, and we'll overcome them in silicon carbide too.
So the soundbite that I got from one of our colleagues was, we're using 4,000 terawatt hours now, and in the future, I think he gave me by 2050, he said we'll need 2,000 terawatt hours just for electric vehicles.
That's right.
Those numbers are a little staggering.
They are.
But it sounds like we're on the road to figuring it out.
I think so. The fact that EVs are expected to add 50% demand to the electricity that we're using today is indeed alarming. But it gives me some hope, because the adoption of EVs is going to drive us to modernize the grid.
Right. We won't have a choice.
Exactly. So at present, we're aware of a slowdown in electric vehicle adoption and purchases. So that's the macro sign that we see. But if you pull back the curtains, the adoption of electric vehicles in the United States as of last year was, I think, about 1.5%. And then a lot of industrialized nations are between that 1 to 4% adoption range. And yeah, you have an outlier in Norway, 25% adoption.
They love their Teslas.
But the point here is, we are talking a lot about EV slowdown right now, but we're just at 1 or 2% adoption.
Right. This is just a blip.
Barely scratching the surface. I don't think anyone doubts that electrification of everything is going to happen. That certainly includes automobiles. And yeah, I think that's going to drive us to develop these technologies to modernize the grid, because they know we're not going to have any other choice.
Yeah. No, and the one thing that you brought up, I think, is apt. When people think about electric vehicles, they think about a passenger car.
Yeah.
Maybe even a pickup truck. Yeah. I've seen some reports from your colleagues regarding gigantic land moving and mining equipment.
Oh, yeah.
I've seen some reports of combine harvesters that are all electric. Then you're getting into the smaller stuff like scooters, electric dirt bikes. I mean, it's the whole idea of electric vehicles is not get in, buckle your seatbelt, and take the kids to school. I mean, we're talking about a whole scale shift in transportation.
Right. Electrified trains.
Yeah.
I mean, electrified aircraft. We have a number of engagements with eVTOL. Mm-hmm. That's electrified vertical takeoff and landing. Yep. Air taxis, mm-hmm. A lot of people call them. So yeah, I mean, everything is being electrified. It's not just passenger cars. It's our transportation segment entirely. The delivery fleet, UPS, FedEx. It's all
Amazon. Yeah,
Amazon. It's all moving that direction, and we can't forget that we got to charge these things.
Yeah, because we don't want to have wires driving down the street, right?
Right.
Kevin, this was great. Really appreciate your time. Really appreciate you joining us.
You bet.
Dr. Kevin Spear is the Silicon Carbide Technology Director at Microchip Technology. He specializes in the materials, device, and process of silicon carbide power devices and their packaging. He joins us today from our global headquarters in Chandler, Arizona. Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.